welcome to our tutorial on what benchmark can teach us about AI-assisted game design. And it's Vanessa who did a lot of the work and me just talking about it, at least for a bit. And yeah, first want to give you...
Why did I organize it if you're not using it?
Yeah, but you don't organize it for you, not for me, right?
Okay, I'll give it to you.
No. Does it work somehow, putting it there? Remember it. Okay. First I want to give you a short overview on what is going to happen in the next 85 minutes, so not 90 anymore. So we're talking about a bit of motivation why we want to have benchmarks, in particular from a game developer's perspective. So why and how to analyze PCG problems. Then we want to talk about the benchmark themselves. So if you have given a problem, how to compile a benchmark. And the solution from our perspective is, of course, the GBA, so the game-based evaluation.
Game benchmark for evolutionary algorithms.
Thank you. Game benchmark for evolutionary algorithms. And kind of highlighting what kind of analysis is possible and which tools are provided within the benchmark. And then we're talking about a bit of the results that have been received with that, and yeah, trying to also provide some kind of perspectives on how to look at the results and how to, well, do your research within that GBA. If you want to join the coding later, you should make sure that you have an account on codeocean.com, and we are going to download or start a Capsule.
So yeah, if you want to follow along, you can just look at it in a browser. If you want to actually do the coding, you should register or download as a Docker image. So in that case, you should have Docker and Python 3.
Okay. Yeah, so we're just turning towards the first part, which is why analyze PCG problems, and that's a kind of a bit of a motivation. So having search-based procedural content generation is a very popular approach to generate various types of contents, and it hinges on specific components, which are too small to read, but we have a larger version of that graphics later on. So you need to find a suitable representation, for example, for the content, and you need an algorithm to search for the best representation, and you need a fitness function to guide the search somehow. So these are kind of three preconditions you really need, and the PCG hinges a bit on that. So the research so far is focusing on one particular aspect of the problem definition, so not kind of considering all the aspects that are possible. So different components that are where you don't focus on, that kind of keep constant or treated as a black box, which could be done, but is not the ideal solution for working with PCG. So taking a more holistic approach has several benefits. For example, a better understanding of the fitness landscape that allows us to find better algorithms, and knowledge about global optima can help assess success on PCG approaches. So we hopefully find better content. And for that, of course, we want to take the benchmarks as for a systematic analysis. And of course, we take the game benchmark for evolutionary algorithms, so the GBA, which allows us to gain a more detailed understanding of the given PCG problem, and yeah, provide some example on how to improve the PCG algorithm. Okay, we have some this hands-on approach. So we have some examples from Mario level generation as well as CoG, which is a more mathematically defined test case, but
That's BBOB. CoG is the framework.
Okay. And we were talking about how to integrate functions and stuff like that into GBA in the hands-on part, and yeah, what results can be obtained, and will guide you through the complete process of setting this all up. Okay, there are various levels of abstraction. So at the one hand side, we have the actual implementation, and then we provide some tips on how to obtain statistical sound results, and this is all interspersed with live demonstration, as will be done in kind of 10 minutes after we talk about the task. So this is having given a problem, the question is how to compile a benchmark from that. So what is needed? Is there kind of a structured way on that? And well, what about kind of uncertainties? Do we have to consider this? A structured procedure is more or less, from my point of view, given by the way of presenting EC results, for example, in papers. And there has been, well, kind of a technical report by a prominent person here from the community, Mike Price, who has written that all down and put it down to 7 parts, where we start with the research question, pre-experimental planning, tasks, setup, results, visualization, observations, and discussion. Why we're talking about that today is that we want to focus you a bit more on this kind of structured way on looking onto your problem and giving it kind of more theoretical approach and really think about what will you be doing and what is of interest, and yeah, think about the experiments before doing that. So the research question is just, well, a short, a brief name of the question you want to do. It's not really that much. It's just more like providing a headline for that. The pre-experimental planning is kind of more interesting since it summarizes like first investigation, first results, also including negative results, which I personally find extremely interesting. Well, if you have tested like a different parameter combination or genotype or something like that, which really didn't work at all, just please report on that as well. The task is then more, from a statistics point of view, like defining a hypothesis or a scientific claim for that, which can then be proven or not. The setup is like specifying all the parameters you set up for your problem as well as for your algorithm. So very structured, very detailed. The results and visualization then describes the like figures or tables you really provided, but from a more an outside point of view, really describing what you have there. Observation is then, well, a more, yeah, talking about unexpected things that can be seen there, unusual patterns, for example, and this is kind of be very objective, while the discussion later on is part of the subjective interpretation of the results, and well, altogether, it gives you, as mentioned before, some kind of a structured view on your problem, and possibly on, yeah, more, becoming a bit more clear on which directions you want to investigate, which directions you want to go, and so on and so forth. Okay, next thing I want to talk about a bit is exploitation versus exploration. So exploitation is kind of intensification of search, like searching for, well, in a local area, a local search to improve the solutions in a neighborhood. So for example, if you have kind of function like that, you would have points in there, you would accept all the improvements that are made and hopefully end up in the best possible value of this basing of attraction. Exploration, on the other hand side, is more like exploring new regions, and what you need to do for that is possibly accepting inferior solutions as well. So as you can see here, this is on the x-axis we have the interval from 2 to 8, and here we have that's enlarged from 2 to 14, and we see, well, if we go beyond this maximum, we find a better minimum there. So this is kind of exploring your search towards different region and not just focusing on the local neighborhood to improve your search. How this is somehow connected to benchmarking? Well, we discovered, or we observed, that when starting with benchmarking or starting with investigating a problem, we regularly start with kind of small parameter changes to sequentially improve the results, which is definitely kind of an exploitation procedure, where you have really investigated the neighborhood, we determine it if no better solution can be found, and or the budget is exceeded, and this is very problem-specific perspective on all that. So it's really specific, based on a specific problem. In contrast to that, the exploration is more like considering structural changes in the search as well. So, for example, considering additional parameters that haven't been considered yet, or change the genotype, or something like that. So, which gives you a completely different problem well, maybe not completely, but at least a bit different problem at hand. And well, this regularly stops with turning towards an exploitation phase, or again, if the budget is exceeded. And the interesting thing here is that you don't really specify on the specific problem any longer, but you kind of investigate similar problems and take a look at, well, what may be interesting from a different perspective.
Yeah. And the exploration is the thing that we kind of want to encourage. So, or like what we think would help understanding PCG problems more if you don't focus on like on a specific thing, like a specific use case, but look around and like similar landscapes. And Dan was nodding and looking at the landscapes. So to give you an idea of what we're talking about, I have brought this example. So the right ones are the fun example slides. So we have this function suite, which is based on a previous paper from Gecko last year. And I have to give you a bit of history to tell you what it's about. So it's basically a generator, which is the generator from a generative adversarial network. So it's trained with adversaries, but the important point is it's just a neural network. So you can see it doesn't work yet. You have the generator. There. Oh, it does work. Okay, cool. So you have a latent vector that's input. So we have continuous input that gets put into generator that puts a multi-layer output, and from this we figure out which tile has the maximum value associated with it, so we can put it into a level, and then we have a Mario level to generate. And so this was the idea. It came up during the Dachstuhl, and of course we wanted to write a paper on it. The main idea was the whole generative adversarial network thing, and so what we ended up doing, we had two example fitness functions. One, like very simple one, you can just measure on the level, so how many enemies we have. We have like a target number of enemies we wanted, and the number of jumps. But the fitness functions really, as like for lots, yeah?
Since I'm relatively new to PCG, I did not really understand what is the optimization of...
Sorry, yeah, I skipped that part.
What do you maximize?
These fitness functions. So the idea here was we don't just use the generator, but afterwards we do latent vector evolution. So we can kind of control what levels we get out of it by searching in this search space for a fitness function that we define. So basically you have a space in continuous, or like a continuous space that maps to different levels.
Is it unconstrained, or do you have constraints?
We have from -1 to 1. It is a box constraint, but that's just the way of training it, so it doesn't necessarily have to be constrained.
Isn't there also a whole bunch of implicit constraints that arise from the adversarial training process?
In terms of the search space?
Yeah, it puts you into a particular part of the search space.
Yes.
In theory, has enhanced quality.
Yeah. So understanding that landscape is actually like the point afterwards. But yeah, the idea here was to try to make a search space where you can just walk around and have good Mario levels, and you can control it by evaluating a fitness function and optimizing towards a fitness function.
And every latent vector gives a valid level in the end?
I mean, a level, it might be broken a bit, but it will contain tiles like that.
Not necessarily playable.
Yes.
Yeah, that's the point.
That is another optimization constraint, but that's not search space, that's objective space, right? Yeah,
And
okay.
The word enriched is critical here.
Yes.
So on this level, yeah, you generate levels that may be unplayable.
Yeah.
Okay.
The control over it is with the optimization afterwards, and that's why we use a simulation-based one, so we can check whether it is or not. Yeah. But the generator doesn't really know anything about the levels or how levels look. So, but the point I was trying to make here is we set up fitness functions so we can demonstrate, we can control where we're going, and we find that the levels we generate have lots of jumps or something, but we didn't properly think about all the fitness functions that could be applicable here because we didn't have the time. We were focusing on the generators stuff, right? And we used the CMAS, and because that works out of the box, but we didn't properly think about it. We used one fixed latent vector dimension. We averaged over 30 different simulations. We just used one level. But because, that it does make lots of sense, because the point we're trying to make is we can do this and propose this new approach of generating levels. We weren't trying to explore all the different possibilities, because it's never going to fit in a paper. We found it's a promising approach, but we don't really know much about the landscape. So we don't know about all these constraints of playability. We don't know how to enrich this and what areas are good levels. So that's why I extended this for my thesis a bit. So instead of having 2 fitness functions, I now had 84. This was created by looking at related work. So there's this paper from FDG in 17, I think, about evaluating platformer levels. So I just put all of them in there, so because then we can evaluate all the Mario stuff. There's also some variations in there because I added some new training level sets. So we previously trained only on level 1.1, but then I added all the overworld levels separately, the underground levels, and both of them combined. And we put level segments together, so there's huge variations, 84 functions, a lot of functions, lots of time running these things. I added, yes?
I'm just wondering what's the reason for not using something like expressive range analysis, but the sheer number of dimensions?
Say again, sorry.
I'm just wondering what is the reason for not using something like expressive range analysis, like Gillian stuff, I think. But the sheer number of dimensions you would have to look into. Because you want to get an idea of what your search space actually looks like and what features it has, right?
Yeah.
If you find a number of features, you do your expressive range analysis, and you have like a really nice visual tool to see what it looks like and what it offers to you.
That is, you can do it based on this data. Without, you need to define the expressive ranges, the features you're doing, right?
The meter features, yeah.
Yeah. So, you can do 2 at a time. Usually.
3, maybe.
Or 3, yeah. No, that's completely, but that would be the post-processing part.
Okay.
But because I couldn't decide, well, this function that one proposed is really good, I just put all of them in to generate some data, and you'll see in the next slide we'll narrow it down again. And then, because we have all the data, we also have put them into bi-objective function, and that's exactly what you're talking about. We then combine them into conflicting 2 objectives. And we didn't do the expressive range plot, we did it with multi-objective optimization, but it's the same thing. And specifically putting them in the benchmark, that's way later in this talk, we have the data to do all these plots in terms of expressive range. So, this is exactly the same. It's not the reason of not doing it. We're explicitly trying to do it, expanding, not just exploring something in one objective, but in several spaces. So, yeah. So basically, we added lots of, I added lots of fitness functions. I put all my optimization algorithms on there, so we have different results too. We trained new GANs with different latent vector dimensions, and we found even lower ones work really well, so we didn't even need the 32 one. We stuck to the number of simulations, and so we have lots of interesting findings, and there's like lots of exploration, like putting the different objectives together. But there's so much data. It's like 84 functions. It takes forever to run. You don't even know where to start. So for the recent public...
How did you come up with this 84?
By looking at related work, putting all the different objectives, functions I found there, I implemented them, put them in there, and then I did some combinations of some variations between them, because I added different, so an overworld level generator and an underground level generator, so these can technically multiply the number of functions I have. I try to be as diverse as possible in terms of fitness functions, but there's like no way of really finding out, oh, this fitness function is missing. So I try to include as many as possible, really.
When you have such a large space of fitness functions, like, would you actually find a solution? Like when you're optimizing?
It's not at the same time. It's like separate problems.
This is not multi-criteria
No.
optimization.
Yeah.
This is 84 different choices of things to optimize.
That's where it's
Yeah. No, it's a set of different fitness functions, and we combined them into bi-objective ones, but that's where we stopped.
Oh
So
my
not.
God, you can do 84 criteria optimization.
Well, not yet.
Well, you can. But,
I can't. Anyway, we restricted this a bit down to 24 then, because for the publication. Yes.
Because you had to, or because you threw out ones that were similar to one another?
Yes.
The second?
Second, latter thing. We found some are the same, some are very uninteresting because they're like solved very easily. We just threw them out.
Have you thought about doing a factor analysis to see which dimensions account for a certain
Yes,
amount of
that
values
is-
to throw them away?
Very late in the talk, but yes, we have. But the point I was really trying to make is you want to maybe go from like one specific problem, you extend it a lot and think about all the different possibilities you could be looking at it, then maybe like restrict it down to focus on some specific things, and that's what we did for the paper. And this was just to illustrate what Boris was saying. We're going to get into the actual the analysis and what we found on all the problems in the very end of the talk.
not sure that we make it.
Okay, you go.
Do it.
Yes.
So you guys practice this a lot?
Yeah.
Okay.
We didn't expect all your questions.
Well, to summarize that a bit, what you actually need to create a function suite. You first, of course, need kind of an optimization problem, which, well, in the content of this conference on GBA, it should be somehow game related. And then you need to scale this problem with respect to the dimension of the search space. As talked about a bit for now, the different functions to be considered. Different instances, where instances kind of means shifts in search space as well as in objective space, and these are randomly done while the optimization process, so you don't know beforehand where the optimum is located, which value it has, something like that. And last but not least, some kind of a handling of uncertainty strategies. So, well, the easiest is the resampling, where you have simulations per points. Okay, then we turn to the GBA. We have not only the Mario gun problem inside there, but we have a top terms problem. I hope you all know this top terms popular game, card game, where we have an input vector here as well, which decodes or encodes cards, or the whole vector encodes a deck of cards. Then either by simulation or directly we have some kind of fitness functions, and that can also be combined to bi-objective fitness function as well. This all has been presented at Gecko 2016. And in particular, talking about the input vector, here we have 4 categories and 4, so the number of categories times the number of cards is then the dimension of the problem, and well, the actual values provided here are values in each category on the cards given. Then we have functions like the win rate for the better players, or the switches of the trick winner. So, well, it seems kind of obvious to us that the more switches of the trick winner we have within one game, so the more interesting the game is. So, kind of, yeah. And yeah, then we have a set of different functions like these, and we combine these conflicting functions. I mean, some of them are not conflicting, some of them are conflicting, and it just makes sense to combine conflicting ones to a multi-objective problem suite, so multi-objective problems. So the instances here are kind of themes for creating for the create decks, where we have to define a lower and upper level for each of the categories on the card, and these bounds are generated randomly, so that makes the instances here. Then we have the Mario Gun function suite, and we talked about that already. We have the latent vector here, which runs through the Mario Gun and provides a level. Then we have 2 different agents that play the level, and either directly based on the level, you have a fitness function, or based on the AI working on that. And again, we have conflicting objectives combined to bi-objective suite as well. So the input vector is specified by the latent vector for the gun, and we have functions like the enemy distributions, which can be directly computed from the level, or we have something like airtime for different agents, which is then computed by the simulation. And combining the combination of conflicting functions is again built for the multi-objective suite and suite. Sorry, and talk about instances.
By GAN, you mean generated adversarial network?
Yes. So there's one thing that Boris kind of glossed over, is the number of the instances that need to be generated, like are part of this benchmark. And I just wanted to give you an example again of what this could mean. So the idea behind instances is that you basically have the same function, but different landscapes, so slightly shifted in some way. So if you average over the performance, you could have an idea of the general performance on this type of function. So because, like, if I have a sphere function that's centered in 0 and I accidentally start at 0, that would give me a very good performance, wouldn't really indicate how good I work on sphere functions. So, so if you start thinking about this type of approach, it's relatively easy to think about it in sphere functions, but if you have a whole PCG system, how do you express this type of function? And so this requires some sort of thought, and in our case, we use the training seeds for the generative adversarial networks. So the idea is the generator is basically a mapping from latent space to a Mario level. And if I start the training with the different seeds, I get a slightly different mapping. So the same point in search space will result in a different point in the level space, basically. Or like the same point in level space will be a different point in search space. So we tested this later, but basically we have the same type of optima, we have the same type of levels, they're just in different points in the latent vector space. So I have to go to a different point to find the same optimum. And that's how we came up with the instances.
Okay, and here's a short overview on the dimensions, functions, and instances, as well as simulation score points we have for the four suites. So we have the top term suite, single objective and bi-objective. The dimensions are all the same for both suites. We have 5 functions here in the single objective case, 5 as well in the bi-objective case, 15 instances each, and 2,000 simulations per points. In the Mario gun, we have either a dimension of 10, 20, 30, or 40. We have 28 functions in the single objective suite, as well as 10 in the bi-objective suite, 7 instances each, and 30 simulations per points. Well, this was actually the state of the art before Gecko 2019. At Gecko 2019, there has been an extension to the suite, to the benchmark suite, and in collaboration with Ivan Bravi, there was the Splendor game put into that by Vanessa and Ivan, and using his Rinascimento engine. I'm not sure how to pronounce it.
It's Italian.
But, well, we haven't fixed the details with respect to dimensions, functions, and so on yet, so that's not within this slide.
Quick note, that's actually not PCG, that's hyperparameter optimization, so mixed integer optimization of game agents, so it's a different application as well. And he's presenting a paper on this, I think it's Friday, on like just the game agents and the engine.
Yeah, so you should go there, it's interesting. Okay, and since all of the game problems are somehow connected with noise, we wanted to talk about uncertainties for a bit. So there are 4 sources of uncertainties described in EA research. The first one is noise, where the fitness function is noisy and different values for the fitness function are provided each time you evaluate it. So, well, if you're lucky, then there's a certain, well, nature behind it, how this numbers are generated. If you're not, then it can be completely different. The second source of noise is robustness, which means that, well, having your optimization process finished, then the design variables will define a certain optimal value, but if you change the design values only slight a bit, then the fitness function may vary in, well, huge amounts. So this is kind of a robustness considered here. Fitness approximation is the next source of uncertainties, which means that your original fitness function might be somehow approximated by a surrogate or a meta model. And the next or last point is a time-varying fitness function where, well, the whole fitness function and in particular your optimal value revives over time.
I have more examples. Maybe. But why are the notes not there?
I don't know. Okay.
And what is the value in the context of this latent vector level generation? And what's the difficulty in understanding what the value is and why it is noisy?
Well, that is exactly the point I was trying to make here, but I'm losing my notes for some reason. Anyway, the noise in this case is the fitness function. So this is noise in the fitness function, and this is because the engine is noisy. So if I apply the same actions, the results will be slightly different, but specifically the AI agents are also noisy. So, which we didn't expect is an A* officially, but hey, you also have a noisy A*. And this is a thing that happens a lot if you do search-based PCG, because you simulate things, and lots of things are noisy in there, like the agent and the engine. And the interesting part here is, in games specifically, is that it's usually not stereotypical symmetric noise. like a measurement error, because then the noise is in the actions, and it's like a discrete thing that happens differently, and then you might end up in a completely different path in a maze or like in the gap in Mario. So the noise distribution is very interesting and should be analyzed more, I think.
But if it were a perfect deterministic agent, it would be always the same.
Yes,
value.
then it wouldn't be noisy.
Okay.
So the direct functions are not noisy. They're the ones that are like the number of opponents. So the ones you compute just by looking at the levels. So they're perfectly fine. And the noise we try to usually average out a bit by doing 30 simulations. But we now also added a new functionality where you can handle the noise. So like if you want to just evaluate once and consider it as a noisy point, that you can do too. But we try to average it out.
Yeah, and except for averaging out or resampling, there are other strategies available on how to handle noise, like averaging over space or implicit averaging, or even modifying your selection with introducing thresholds. So your fitness function has to, well, increase for a certain threshold to be accepted within the search, for example. But yeah, I think we should go to the next one.
Got it. But why?
This is robustness.
Yeah, but my.
Yeah, if you go down.
Okay. So for robustness, this is basically noise in the search space. So we had fitness space, and now it's in search space. So that's more difficult to think about, and then I had to think about like finding an example in a bit. It wasn't as easy, so the equivalent in engineering is if you can't refactor the same object exactly. So, right, because you have some issues like when you factor it. And there's similar things if you think about physics engines. So, because of some rounding errors, you might not get the exact same behavior in reflecting rays for some reason, because if you look at Unity, it gives different results all the time, even if I specify the same shape in like for object colliders, for example. So you get some uncertainty there. And one point is also interesting is you might want to consider some slack for the for customization. So the point here is I might find a good level, but I want to find a level that you can vary a bit, where you like shift the gap a bit, and it still has the same fitness function. So that would be like a robust optimization in Mario levels. Yes.
There's a wonderful paper called Survival of the Flattest by Chris Adame. It's about finding optima that aren't necessarily the highest possible, but they're on big flat hills. And
yeah, so it's basically safe to shift around a bit.
Yeah. Okay. Again, there are different strategies on how to ensure robustness of your solution. Since the problem is kind of related to the noise problem, while the noise problem is applied to the fitness values, where the robustness means uncertainty in the design variables, you can nevertheless apply this resampling or averaging strategies, and there's also a multi-objective approach considered or proposed, where you have the expected fitness function as well as the fitness variance as considered as different objectives, but okay, we don't go into detail here. We go into less detail on the other two sources of uncertainty, which are rather complex issues and kind of defining their whole research areas themselves. And, well, believe me, you don't want us to elaborate on this now, since time is running out.
But I do have examples.
Exactly.
So fitness approximation is basically when you don't really know the fitness function you're trying to optimize. And one common example is like the ones we showed. We're using an AI simulation to measure, I don't know, difficulty or even the number of jumps. That doesn't necessarily mean that I know how many jumps humans will make, even as like an objective thing I can measure with an AI. So that's already approximating the fitness function I actually want to look at, but then there's also, these functions are also expensive, so you might also want to approximate them with surrogate models instead, and then you have even more uncertainty around it. So that's like, for the fitness approximation, that's really important, I think, in this space. And for time-varying fitness function, that's also very interesting for games, I think. So if you're trying to optimize the hyperparameters of an AI, but then your meta changes, so you might need to react to different opponents, or like even the content and the meta changes, like people react to it, and then your fitness function might also react to it because you wanted to create the most difficult AI or something, but then people improve, or you want to do dynamic difficulty adjustment, someone improves, so you have a change in my fitness function over time.
Okay, and that more or less finishes the first part of it.
Yes, now it's the actual practical part.
Yeah.
So we've been talking about this GBA for a while now, and Boris introduced the function suites. So now is the part where we get to how can I actually use this to do what I wanted to do, or like what the main motivation of this was. If I have a PCG problem or like any other problem optimization, how can I use the tools that are provided within the GBA to analyze them and learn more about your problem, which might be generating Zelda levels or something. So the GBA has been built on CoCo, and CoCo is short for Comparing Continuous Optimizers. It's a relatively well-known benchmarking framework within the evolutionary computation community. It doesn't even only do continuous optimization now, it also does mixed integer, so the name is maybe needs to be updated. But it provides lots of different features. So if you can see here, it has different interfaces for your algorithms. So it's intended that you can plug in your algorithm very easily with all the different interfaces. We now have another interface with a socket, so you can plug in even more things. Then you run some experiments, and the results are all outputted in log files. And because it all goes through this framework, they're all formatted the same. So then there's a post-processing thing, which can read all the log files and plot them into pretty plots, which we'll look into in a bit more detail in a second. So the idea was to build on top of this. Like, we already have all these interfaces and the post-processing capabilities, and we just wanted to add more experiments, and that's what we did with the GBA. So we have additional experiments here, and what I will show you now is how to easily add your own experiments there, so they can make use of all the post-processing capabilities, all the existing interfaces, existing ways of sharing your results, and existing algorithms, and you just like plug them in together to hopefully encourage this exploration that we were talking about at the start more, to make it more easy, because we can just add the experiments. So now for the actual practical thing. If you do want to go there, I think not many people actually have their laptops with them. So just let me know if I should be waiting. If you want to actually code and follow along, because we do have some time left. But if you go to this link, or scan the QR code, or even go to CodeOcean. You can just search for GBA here and you should find it. So what is this code ocean and why should you sign up for it. Where's my dashboard? It's it's a platform where you can put all your code and your results from papers that you published to make it easier, especially intended to encourage reproducibility. So ACM and IEEE, I think both are encouraging using it, and I have it in this tutorial as a way for everyone to easily follow along and avoid having to install things, because what this basically is Docker images. So you have an easy way of creating Docker images, and they also run on their servers, so you can just like execute things and see how they work, and then you can modify things a bit and see what happens if you'd run some slightly different experiments, which is perfectly suited to this case here. So you can create them privately, but then you can also publish them, and this is what we did. This is why you can find the GBEA. And you can see the associated paper as well, and then you can click on it, and you have a published version. And then if you're following along, you should have a button where you can edit the capsule. This creates a local copy for you. I actually can edit the original because I have the correct rights. But yeah, so if you want to follow along, just click on this, and you should have access to the capsule and be able to modify it. Actually, can't. It's obviously not intended for this type of resolution, but that's okay. We will make work. So what you see here is previous runs, and the one for the published console are slightly different. Okay, I'll just go through them. So if you click on the metadata, that is the paper that is associated with it. You can find it on there. If you want to read up on things, you have this environment thing, which is I just want to make it bigger.
Size, Scotty. I need more size.
Oh, is that readable?
Just barely.
It's a bit better, actually. So anyway, it's basically it creates a Docker image, right? So you have all the requirements in there. So if you want to recreate something locally, and you can either download the capsule, export the capsule to Docker, or you can also like read up on all the requirements, which makes it really easy to also have this preserved for posterity, because I know what all the requirements were where it did work. So you can also have a Docker file, which is generated automatically. In this case, we have a post-install script which downloads the code from GitHub and checks out the branch that's relevant and builds everything. So this should work. The baseline here is we have, the thing that's run is this run script, and it can first of all reproduce the state of where we were for the Gecko paper. So we have the GBEA, and it can execute experiments on the GBEA. Whoa. So if you want to follow along and do this, we can first of all set all this part to false. This is like additional stuff. But we can run the BB suit, for example, with, so this is line 24. It first starts up a socket in Python, and then runs an example experiment which can run all existing function suites. So the BBUB suite is an artificial function suite. We have the GBA ones are in there. So we can do this, save it, and then you can just click on reproducible run, and then it should do things. So sometimes it will automatically build, but this one is already saved, so it doesn't need to build everything from scratch. It just executes the GBA, or like CoG. This is CoG's output, so it works automatically. You didn't have to install anything. Everything's great. It executes all the functions that are in BBUB, and it's the same for Mario, so you don't need to install all the torch stuff that's required there. You don't need to install Java or handle the versions. It just runs the thing, which gets outputted into log files. And why it's still running is it's also generating the post-processing files, so the plots that I will get into a bit later. But if you look at the published version of like previous results, you can see this is in this area. You see the results that are generated, and you can just download them if you need them. So while this is running, this is basically reproducing the state the way it was. We can execute BBUB, we can execute GBA if you want to. Now the point of this tutorial is how do I actually put in my different fitness functions in there to work with the whole thing. So what we do is we wrote some scripts to generate all the files that are required to do this. This hinges on a definition of a problem. So let's say we have this problem, what we want to put in the benchmark, where we just add the different points in search space. So add the search space point, and so add all the X values in the search space to get the output. So there's this example script already existing, but here, so you have an evaluate function. But in this case, let's say we just want to add a different function where we don't add the absolute values of X, but just use the sum of all X values. So I could edit this script simply, or like replace all the different functions with whatever you're doing. So we say we have a function free, and instead of adding the absolute values, I want to now add just all the X values together to get my result. And so you can do this in Python, you can also do it in C, but I'm showing it in Python. You have this existing template, you can just modify it to, for example, in my Mario code, I just call the existing Mario evaluation stuff in there. So this is the evaluate function. I added function free. I can save it now. This doesn't immediately mean I can execute it. There's like a few extra steps required, which is generating all the files that are found in this suite folder. I will delete it now to show you how it works, because it can be generated automatically. To do that, we have this create suite script under utils, where it will create some dummy files, so you don't have to deal with all the different files that are required to put it into CoG. So I can put in a name for my function suite. I might call it, well, it's tests. We can call it CoG 19 or something. then we can specify all the different dimensions in search space that we want. So we might want 2, 5, or 2 and 3, for example. We have the different number of functions. And I just added a new function, so we now actually have 3 functions to look at. Instances, we have 15, which is fine. I mean, you can set these things to whatever you need. Same with the lower and upper bounds of the search space. These values you actually the BV and NV values you only need for bi-objective. We're doing single objective at the moment, so we don't need it. This is the number of objectives, so we have single objective. And this is just for logging purposes, so we can ignore that safely. But basically, you just need to set all these parameters to generate all the files that are needed. So how do I do this? How do I execute this file? You can go to Launch Cloud Workstation and the terminal. This will basically put you on a machine that has all the requirements installed. So you then get the console, and you can execute this script that we created. And then you can shut it down. And it should have recreated the whole folder with the function suite in it. So we can open that up now. It has a folder because we named it the function suite CoG19, right? So it has a folder CoG19, which contains my evaluation script. So the one that I created previously with the added function 3. It creates lots of other functions, C files that are required for handling within CoCo. They're not that interesting. You can change them locally though. So if you, for example, I don't know, change your mind later and want a different lower bound, you can edit it in the file and it'll be recognized. But for example, you can also add infos. So we can just try this so the new function we added is the CoG19 tutorial function, for example. We can name things and change them locally so they exist in there. And that's basically it, to at least create some dummy functions that will then work within the whole benchmark thing. So we have all these functions and then have a second utility script which will copy all the generated files into CoCo and rebuild everything. So then you can use this script, this new function suite. And you don't actually need to take my word for it. We can just run it now. So if we go back to the run script, we previously executed BBOB, right? So in this case, we will want to execute the newly generated suite, which is RW, which is just a prefix to keep things consistent. We named it CoG19, and it has, and it has one objective. So it's -1. This is the name of the newly generated function suite. And we might want to execute it for a budget of 10 per dimension. Then we need to set use local to true. So that then it will copy all the files that are generated and rebuild everything. And then I still can execute it and execute the post-processing. So let's do this and hope it works. This will take a while longer because it's rebuilding everything. But this is just to show that with like a couple of edits to the fitness function, you can plug your whole thing in there, especially if you're using Python. So it's doing things. This is the CoCo build script, and this takes a while. Okay, so now we see it ran functions 1, 2, and 3, so it did pick up on the fact that we added a new fitness function. we also put in dimension 2 and 3, so it ran in dimensions 2 and 3. It's done now, it says, and it's automatically creating some plots. So, oh, it's actually, oh yeah, it's done already. So we have the results already, which is good. And as I said, we have these log files here with all the results that it logged from the benchmark on this new function. So we could have, so we have function 3 here, which we added newly. And currently it's running random search, but you can plug in the CoG framework, it's easy to plug in new algorithms. And it also creates this post-processing stuff, which are the plots. So I will give more details on the post-processing, how to interpret in a second, but just wanted to show that if you remember, we added, we added the new name for the function 3. Probably can't see it properly. Oh, maybe. Ah, okay. If you remember, I edited this one file with the name of the function that actually shows up here, right? So it's whatever you edit locally, it will be put into CoG. And the plots are not nice now because we just had so few, a small budget. That's why I will go through the plots in a second. Should we do like a question thing now? I'm not sure how many of you have been following along, but the main point is you just need to edit the evaluate function and then it'll be in there. And as long as you have some Python or C interface, it'll work.
Yeah, I mean, the interesting thing is that we have all the post-processing in here. So it not only generates the data, so you also have different ways of visualization and looking at the results. And well, what's running in the background is running one algorithm now on different functions, on 4 different dimensions, 4 different instances, and so on and so forth. So that what takes a while. And all this kind of handling the results, that all the data is somehow taken away from you, and you just receive the plots and the results for that, which can then be used directly in a paper, or well,
yeah, they
taken
even
for investigation.
They even have LaTeX templates, so you can actually generate papers automatically if you want to.
Yeah.
So let me talk you through the plots that we just seen, which weren't that pretty yet, because we haven't run full-scale experiments. For that, I need to do some background, which is the way that performance is measured in CoG. So first of all, the idea is to have the performance over all the different budgets. So you don't specify, I want to run it for 100 function evaluations per problem, because you might not actually know in advance what budget you have. So for all budgets, it basically records how good you were. And the question is, how do you measure how good an algorithm is? There are 2 main approaches, which is like this fixed budget, and then you figure out what function value you reached. That's not actually the approach they take. They use a target-based approach. So you can specify, oh, this is the next milestone. So for example, like a playable Mario level, and then the next one is a Mario level that takes longer, like longer than 5 seconds to finish or something. And then you can measure how many function evaluations you needed to get to this Mario level. And this is the evaluation measure they use for all the plots. So just think about it in terms of anytime performance, like how long do I need to get to these targets? And which brings me now to the plot.
Sorry, so the y-axis was the numerical value of the target,
whatever quality indicator you're using. So in single objective, it's the fitness function. In multi-objective, it might be hypervolume or something. So it's whatever you're looking for to optimize.
Okay. Could you elaborate a little bit more about the multi-objective?
So in multi-objective, you can't. I mean, the idea is to be able to balance between multiple objectives, right? So there's a bunch of quality indicators that have been developed, and they discuss about them all of the time. There's like not one that they've been using.
This is still an active area of research.
Yeah.
There's no consensus about quality of technique.
Yeah. So there's just one thing is the hypervolume, which is like Boris's favorite.
Very prominent, yeah.
Yeah. Which tries to measure how the Pareto front is basically sampled. So if you have lots of like extreme solutions, but also solutions in the middle, then that will be higher. But I mean, this is not actually important. It's important you know what to optimize, and then you can define how the targets, and be like, oh, I got this close to the ideal solution I was looking for, and then you can record how many function evaluations you needed to get there.
But what are the conflicting levels in the Mario level generation, as the conflicting objectives in Mario level generation? Just to have an example. I mean, I know what multi-objective is, but I don't know what it is here in game-based.
Do you have the slides for that? No. So one example I think Boris mentioned was we had airtime. So if you're running, so the idea is to maximize the time it takes for Mario to finish a level, just to make the most of a level, right? But at the same time, we want to make it playable. So the more difficult you make it, the longer it will take, but it also might make it less playable, so then you have a constraint there. Also, you might want all of the level design is basically around trying to figure out balancing different objectives, like making it difficult but not too difficult, and making it difficult enough. And we have, Boris just gave me the examples that we actually put together. So one of them is M4 versus M6. Where's the list of different apps? Okay, so that's transition, distribution, and decoration frequency, which is so one of the things that I was suggesting in related work is the decoration frequency. You want to increase the number of pipes and goombas in there, but then you make it more difficult, and then you might also still want to have a good level, so that the leniency, if you want to minimize this, for example, you want to make it easy, but want to make it pretty. So the decoration frequency is, if you optimize it, would add a lot of pipes and a lot of enemies in there to make it look pretty, but you want it easy. So if you, the leniency would reduce the number of enemies and pipes and everything just to make flat levels. So that would be an example. But I mean, it's more about, we're not focusing too much on the GBA here. It's like whatever problem you have, you can put in there, and then if you don't have conflicting objectives, you don't need to do multi-objective optimization. You can just do a single objective.
Yeah, the hypervolume in that sense is only a function to put the different objectives mapping to one objective.
Yeah.
For the
Okay. Anyway, going back to the plots. I just wanted to give you an idea of the output that you might expect from all of these experiments. And to do that, I used the existing data they have in CoG. So, for example, we can click on the random search here. My favorite page is this one, because I understand it most. But it's also the easiest one.
Is it?
Yes.
Doesn't look like.
Yeah. So you have the functions separately here. So you've seen this, the equivalent here from what I generated previously. So this is the sphere function, and they've been running random search on it. So these are results for random search and in different search space dimensions. So the higher the point, the better. So it's the percentage of targets reached. So the closer you got to the known optimum, then you are at 1 and are really good. Random search doesn't do that, so it's not at the top. And on the x-axis, you have the number of function evaluations per dimensions it took you to get there. So at the start, everyone's low, and then if you evaluate a couple of times, you reach more targets, so you get closer to 1. And here it's a comparison of the different search space dimensions, and they have these types of plots summarized over various different things. So in this case, it's for dimension 2 and different functions. So apparently function 5 is way easier to optimize with random search. I think that's linear slope. So linear slope is good. Random search is good for linear slope. At least it's better than for the sphere function. But the point is, if you put in your own function, you know what you're looking for. Like, you know what these functions are, and then you can look at them and you can see how long it took to get to the optimum or to improve whatever targets you specified. And the cool thing now is you don't only get this for one algorithm, but also as a comparison. So I, in this case, ran 3 different algorithms, and they can also be compared. So if I click on the same types of functions, on the same type of plots, it now compares per dimension, but it compares the different optimizers. So as you would expect, random search is not doing as well as the actual optimizers. And it also puts in, so you have the option to put in the baseline as the best 2009, which wouldn't be, this is just the baseline for BBUB, but if you're generating a function suite, you can also put in the baseline performance and see whether you can improve it or not, or get to that performance. So yeah, these are the main plots that we have. And it does show you how long it takes, so anytime performance, how long it takes to get to the optimum. There's a lot of things to explore here, so I will just show you quickly. There's a scaling with dimension thing. I won't go into detail here, but it's because you run in different search space dimensions and have the data for everything, you can compare divided in relation to the function dimension, how long it took you to get to the optimum. Because it's the similar problem, just so, for example, here's the sphere function, but just in a different dimension. Does your approach scale up now if you add more points in search space dimension? And that's the plots to explore this. If you are flat, you do linear scaling, which is fine. If you are these slopes, do quadratic scaling. If you're worse than that, that's concerning. But this is a way to control the scaling. And you also get nice tables which automatically do statistical analysis tests on what algorithm performed better in terms of what targets. So you don't even need to do them yourself. You can just look at those.
I mean, the interesting thing here is, again, that, well, with having put the GBA on the CodeOcean thing, you can easily plug in your own algorithms, you can easily plug in your own problems, and you get all this information with, well, on different dimensions, on different instances, and so on and so forth, for your own functions and using your own algorithms. I think that is the main message here.
Yeah.
And what is even, well, what brings us to the result is that all we showed by now is kind of this exploitation thing that I mentioned in the beginning of the talk, and you will now come to the more explorating thing.
Yeah.
Like changing up.
So you don't need to use the post-processing. You can also just work on the data. And what I'm going to show now is going back to the Mario example and some anecdotes of, so going back to what we started discussing at the start, like what we found, how we kind of narrowed down the function suite, what we learned about the algorithms, about the functions. So the first anecdote I have is, I mean, we started off, if you remember, we started off with this paper and we used CMAS and it seemed to work fine. We didn't actually realize there was lots of noise because we thought it was deterministic. And it has a weird landscape. I think there's this paper by you too, which like about the weird landscapes that sometimes exist in the automata, which also has like the weird...
I would say almost always, but yes.
Yes. So what we found, unfortunately, is that all the algorithms we tested, which includes random search, perform pretty much the same. So we didn't even need CMAS. We can just do random search. We can still control it, kind of, but because it wasn't, for some of the fitness functions, wasn't that difficult to find a good enough level. But this is obviously some things we should have looked into before we published the paper and figure out whether we actually need CMAs in the first place or not. And because we just ran all of them, it's easy to figure out now. We can just compare them. So this is in terms of, CMAs. The robustness, yes?
Even Chen at York University is like the high priest of always benchmark against random search. Yeah.
Yeah, see the thing is, like, we're not, I agree, if you're doing an optimization algorithm, but we were not proposing an optimization algorithm, that's why we weren't thinking about it, right? But, I mean, but the point is exactly right, maybe you should be thinking about it so you understand more of what problem you're actually posing in this case.
That was random search beating all other algorithms in one of the competitions yesterday?
Maybe. I mean, the thing is, CMAS does still improve things, but you can also be very lucky. Apparently, there's just lots of lucky points in there. So, anyway, robustness, if you remember, I talked about the different instances and figuring out when I retrain the generative adversarial network, does this completely screw up my space? So if I do my experiments just on one generator, I can't really talk about generalizing this approach or like that it works in general. So we introduced these in instances where we used different seeds to optimize, to create the generator, and did the whole experiments on all of these different generators. And we found that this is actually, these instances are pretty robust. So independent of where I start my training, I basically get landscape with the same objective values. So it doesn't matter where I start my training, I get consistent results, and I can get at the similar quality levels, which was good to know. So this is great. Another thing that wasn't that great is where we started looking at the results more. So I optimized all the different functions and looked at visually at the different outputs. So the points in latent vector space are different, but then what kind of levels are they creating? And this is an overlay of two different underground optima that we found in two different functions. So one is blue and the other one is yellow, and then the overlap is green, so they're transparent and overlaid. And if you can see they are very similar. So there's not lots of novelty. If that was your point, to create different diverse levels, then you probably failed if you do that. And this just made us think about the training samples we put into this. Because I think, especially for the underground levels, we only have 2 underground levels in the video game corpus, and I don't think they're enough. They create very similar levels. Which, yes?
Do they have similar fitness?
They're for 2 different fitness functions. So they didn't have the same fitness. But the thing is, we didn't find this out just by randomly sampling the space. They didn't, the levels look differently if you just like do random sampling of the space. But because we now know where the optima are of different things, they look very similar. So that's a good thing to know about your PCG problem, that it basically results in the same levels all the time. That would be good to know. The noise, right. So I said we didn't know about the noise. We then started investigating it a bit more based on all the function evaluations that we logged. And we found very interesting patterns here. So you see the red ones is the maximum difference of all the evaluations for the same point. And you have the maximum, the standard deviation of the fitness value. It doesn't actually matter what function this is, because there are similar patterns in there a lot, which is these little arcs. So if you have low fitness, whatever it is, it's mostly like based on progress, so how far the AI got along the x-axis at the level. So if it fails a lot, then it fails consistently. If it always makes it, it makes it consistently. But in the middle, there's lots of variation in there. So you get varying noise depending on where you are in the search, or like how good your solution is. So if you have like a midway solution, it's more noisy than if it's either decidedly good or decidedly bad. So that's an important point to consider, because we came up with a number of 30 simulations to average over based on random sampling and trying to narrow down the confidence intervals, but we didn't take care of, look at the actual fitness, and then it might be higher in some areas and in other it isn't. So that's good to know that the noise is weird. 5 minutes? We also, as I said, we had different variation of the same fitness function. And this is an example of that. I won't go into detail here, I think. But we basically did box plots to figure out how the fitness values are distributed. And depending, so some of these are underground, some of them are over world levels. So you can see the problems are also different if you do underground or over world levels. Even though you have the same exact fitness measure.
That's serious variability.
Yeah. Then there's one thing that you mentioned earlier in terms of figuring out how different the functions are. We mostly did correlation plots. But one thing we're currently working on is using exploratory landscape analysis to try to characterize the functions and see whether they're different, figuring out the features that are most important and most describe what is going on. Here's just an example of a Disney plot that we made and see whether they cluster into different things. And for this, the outcome is not like completely fixed, but we found that the Mario functions are like one cluster, which is different from the Shekel functions that you suggested, the Foxhole ones, and also from the existing BBOB, so the artificial functions. And we also get clusters around whether you simulate the functions or you do without simulations. So the Mario ones, we have some which just count the number of enemies, or like the spread of the enemies that you do just on the level. And then you have ones that you need to simulate an A-star on it. And these are different in this space at least. So because I have to end it here. These are like all examples that we can learn from it. We can generalize it further as well. So I tried to show some of this already, but for the representation, that you usually in a PCG algorithm you can choose yourself. By having different search space dimensions and comparing them, you can figure out the complexity trade-off. So in the original Mario paper, we did 32-dimensional space, and we found we can actually do get at the same fitness value with this 10-dimensional data vector. which is good to know. And similarly, you can compare all the different fitness functions, figure out conflicts between the fitness functions. Noise levels, I did talk about, which is very important. Landscape information, looking at exposure and landscape analysis. You can finally find some optima, which you can't usually do if you do just random sampling. And then you can zoom out a bit from your concrete problem, even like you explored the space of the Mario stuff, of your area. You can also, ideally, I think that's the vision, can we find some patterns that go beyond just latent vector evolution on Mario? Does it also work on Zelda? Or like if we zoom out even more, do the same patterns hold like in terms of noise or in terms of this is the type of fitness function we have for the landscape automata or something. So if we have more data, and that's I guess the last point I wanted to make, with this putting everything on CodeOcean and having this easily available, we want to try to make the data more accessible so we can compare and get at this zoomed out vision of things. So we have this, it's essentially a Gecko workshop. We have to run the Gecko workshop to get more algorithms, to get people to do all the expensive optimization algorithms. But we also have a website and a Slack so if you want to add your problem, if you want to explore your problem, and the scripts don't help you, just talk to us. It's not like the most stable version of code ever, but we're very happy to respond to it. And I mean, the idea is really to put all the results available to the community, so we can then do analysis on it and talk about it. And that's where I would end. So we are technically out of time. I think we have like half an hour break, probably.
I think so.
So, yeah, do leave, but if you just want to come by and ask questions, do that too.
It works.
That's one. Two, you're talking about maybe finding a global optimum. In almost all these problems, you don't want a global optimum. You want one of the 100 million really good local optima,
Yeah.
and you already know that.
Yeah.
Third, I think I have an optimization algorithm to help with fitness landscapes like this.
Mm-hmm.
Do you want the very short version of it?
Medium short.
Okay, so you have to have a generative representation. But for example, if I'm optimizing a real function, what I do is I say, okay, I can move it along any of the coordinate axes, and I have a fundamental movement length.
Mm-hmm.
Okay? The commands either say move in this axis or increase the fundamental length or decrease the fundamental length. If I land on a long string of those commands, I'm going,
Yeah.
right? Okay, evaluate the fitness at every single intermediate point. The fitness of the gene is the best fitness it found. This acts to enormously smooth the fitness landscape because you're looking at a couple hundred points. Now, you have to be careful to be fair and remember that that was 100 fitness evaluations, not one.
Yeah, and also that it's expensive.
No, it's cheap.
But the fitness functions are usually, if they are simulations, they're expensive.
Oh, I see what you mean. Yeah, this is more
Yeah, if
annoying on an
each
expensive
one's-
fitness function, but like, and for the apoptotic cellular automata, they're sort of intermediate expense because you have to run the cellular automata until it dies or hits the bottom or whatever. So yeah, but the thing is, it turns out that given the base cost, based on my preliminary testing, this is cheaper because it finds something much sooner. And so what you do is you do this, and the fitness of this is the best thing it finds, and then that becomes the new starting point because your representation edits a solution. So when you find something new, you reboot the algorithm. If you don't find something new, you run it as an ES with a very small population, and so you're throwing bolts in all directions. It's extremely elitist and hyper-exploratory.
Yeah.
Now, given that you guys found another one of these goddamn random search may be your best option functions, it would be fun to incorporate you guys. Oh, and the name is lightning optimization because I'm thinking of this as a lightning bolt.
Do you have the code? Because like we could pretty easily plug in.
I have 3 hacked examples that are totally useless. I'm now trying to write the general code.
Okay.
This is, right now, this is 5%, yeah, I have hopeful experiments that I hacked that I don't want anybody to see the code because it would be embarrassing, and about 80% theory.
Yeah.
But the mathematical theory suggests that all this thing does is act as a really powerful smoothing filter.
So basically it's...
So what's the difference to coordinate search?
What is coordinate search?
Well, isn't it a kind of back in the 1960s going along the coordinates and searching for...
Yeah, I remember this. It's also called beam optimization.
I don't know that term.
But coordinate search, you optimize in one coordinate, then you optimize in the next coordinate, then you optimize in the next
Not
coordinate.
necessarily.
Okay.
If I remember correctly, but okay.
I don't know, and I haven't heard
1960s,
of it, so
okay.
I need to look it up.
Yeah.
But no, this thing goes not only in all directions, but that change the fundamental length command, and there's like, make it a little bigger, make it a lot bigger, make it a little smaller, make it a lot smaller. Those are cumulative. So the thing can also, when it gets into a good area, shrink its fundamental length so it searches much more locally.
But so it's an ES with adaptive step size, but like it's
No, it's an ES.
Yeah.
The adaptive step size comes from the fact that some of the generative commands say search on a finer grid, search on a broader grid.
Yeah.
Furthermore, I just gave you the real optimization one. I've come up with an two different infinite families of representations for searching ordered genes that are based on using group theory to get the orders rather than...
That's interesting, because like these representations are like when you start with like complex points in search space and then you just put them in an array and try to optimize it, then I don't think that's...
So, okay, that's the other thing is I have a guy who, his cat died, 2 of his aunts died, he broke his hip, he broke his arm, and that triggered his alcoholism, and all he has to do is finish writing his thesis. His project is representations that arise from abstract group theory, and the big hit is ordered genes, because it turns out that if you use group theory to design your representation, the crossover operators are not disruptive anymore, the way they are in standard ordered genes. And those are natural for... So the representation is pick a generating set for the group. Okay, that's your alphabet. Just go down the alphabet, and that tells you which permutation you have. But that adapts to lightning optimization perfectly. Because you get it anyway. So later I'd like to discuss with you guys maybe putting some of your functions into the lightning optimization research, and as soon as I have it done, you can have it. Hey, does somebody else want to talk to them? So, and that was a fun tutorial. I believe I have 4 things that could become papers easily from listening to you, which is my quality measure for a tutorial.
That's pretty good.
Sorry?
Redemption block for the Mario and so that's not sure.
Okay, yeah.
So for Mario, you said it initially had how many fitness functions are you using for Mario?
I think that'll probably be 84. No, that's 28. 28, yeah.
And then they are mapping to dimensions basically.
Yeah, with the Disney. And that is computed based on exploratory landscape features. So that's a thing that people are maybe do. Should we get rid of that?
I'm just trying to make sure that I'm here in time to set up. I'm not trying to chase anything.
Yeah, like if you want to set up, do that. So the
It's okay.
so landscapes is a way of like doing a data-driven way of characterizing fitness functions. So it does very dumb measures, but by doing a lot of them, the idea is to get a characterization of fitness function. And originally it was used to then use classifier to figure out which optimizer to use. But we're using these measures
Is that the same as like partial analysis? Or?
yeah, but like less manual, more like data driven. And in this case, we just used these features, which are like, I don't know, 120, to then map them to the TISNE.
So each one of these is this single fitness function, so each one of these points.
The points are fitness functions.
Okay, and then they are averaged maybe over number of samples, or is this just for a single list?
These are grid samples. So we have the latent vector space. We do a grid sample with like 1,000 samples.
Okay.
From that we compute the ELA features. So then you have a vector of 120 per fitness function, which is something like the mean value and the, I don't know, what else is there? Standard deviation of, and like these things.
So these are all the things for the fitness function?
Yes.
As well to tell you how good it is for...
In terms of like just characterizing it, yeah. So yeah.
And then this 120 are marked to...
Yes. Yeah.
And why did we expect to see clusters? That's the...
Well, so first of all, the different instances are in there. So the hope was that the instances were similar, right? So we at least expected the instances to be in the same similar space here. So that kind of works out. So if you like the function with the same numbers are closer together. The expectation, I'm not really sure, but we wanted to figure out whether these Mario functions are different from existing functions. Because the idea of proposing this benchmark for the evolutionary computation community is that these types of functions don't exist. And like we have anecdotal evidence that random search works very well, so probably no one has really benchmarked these type of problems, but we wanted to find a formal way of saying, oh, these functions, fitness functions are actually something you're not working on at the moment. And the other point is, if we can find clusters, especially if we put the top trumps in there too or something else, then the hope would be that similar optimization algorithms work on these types of functions. So they're trying to figure out how to generalize what we find on this Mario stuff. Like if CMA has worked for one fitness function really well, if we can have a way to figure out if I have a new problem, this is a similar function, I can use the findings I have on the Mario stuff. But this is like very exploratory